Assalamualaikum and hi. Before start to the presentation BENC 2413 Digital System Group Assignment, first of all, I would like to introduce myself and my team member. My name is Salahuddin Safwan and with me today is Ahmad Irfan, Chia Huan Chen and Yoh Chi Long. Before start to the content, I would like to brief what will happen in this presentation. This presentation is divided into two parts. The first part is about parallel and serial 6-bit by 6-bit multiplier presented by Chia Huan Chen and Yoh Chi Long. And the second part is about to design a digital system that detect a password that will be presented by me and myself and Ahmad Irfan.
I am Chia Huan Chen. Now I will present the part 1. The part 1 needs us to design, simulate, and verify a fully parallel 6-bit by 6-bit unsigned multiplier digital circuit with 1-bit full adder and half adder as building block. Before we design the multiplier, we need to do the multiplication. To design a binary multiplier for A bit times B bit where A is multiplicand and B is multiplier, we need A times B AND gate and A minus 1 B bit adder to produce a product of A plus B bit. Here, A is 6-bit and B also 6-bit. 33 AND gate are required and 5 adder with 6-bit to produce a product of 12-bit. But we have to using 1-bit full adder and half adder, so we need more adder. So instead of 5 adder with 6-bit, and we need 30 adder with 1-bit full adder and half adder. And this is the step of multiplication. That's 6-bit of multiplicand times 6-bit of multiplier and we get the partial product. Let's include carry and sum, and finally we get the 12-bit product. After do the multiplication, now we can draw the block diagram. And this is the block diagram for 6-bit by 6-bit unsigned parallel multiplier with 1-bit full adder and half adder. After draw the block diagram, we can write the Verilog code. If we name the module multiplier A, B, P, and the input A is 6-bit from 0 to 5, and the input B is also 6-bit 0 to 5. Output P is 12-bit 0 to 11. After that, we name the wire from W1 to W84. Since we use structural modeling to write the Verilog code, so we just follow the block diagram. For example, N1, the input is A0, B0, and the output is P0. And we continue write the Verilog code until N66, and we end the module. Next, we will write the Verilog code by using syslin and simulate it. After we write the Verilog code for 6-bit by 6-bit parallel multiplier by syslin, now I will simulate it. Okay. After the Verilog code run complete successfully, we check the error. Since the error is nothing, that means the Verilog code is correct. Now I will insert the input to get the output. Now I will insert the input A with 6-bit binary 000011, and the input B also 6-bit binary 000011. Now I will run and get the output. Okay, now we can see the input A is 6-bit 000011, and the B also 6-bit 000011. And finally, we get the output is 12-bit 0000001001. That's all presentation for part 1.
Serial multiplier, we will first do the multiplication as parallel part, similar to the parallel part, which we will get A0, B0, and then addition, and then we will get the carry on and the sum, and then after we calculate all the things, we will get the final product, which is P0 until P11. And then when we start our coding, we need to build the subprogram first, which is consists of half adder, which is represented by HA, and then full adder, which is represented by FA. And then this is our main program, which is consists of A, B, the input, and the P output, which from 0 to 11, and then A, B is from 0 to 5. So now we continue our running simulation of our program using Synchronous, and then this is our coding for our serial multiplier. And then after we do the coding, we build a test bench file, and then we put our input as 6-bit 00000001, and then 6-bit 111111, and then the another input is 6-bit, and then both is 111111. And then after we put all the things, and then we check all, and we can click this to check our syntax error. Okay, so the syntax, the behavior check syntax complete successfully. So after that, we simulate the behavior, simulate our output. Okay, so from here we can zoom it, and then we can see it. If we use 111111 input multiplied by 000001, we will get this output, which is consists of 12-bit, and then the other input also, if you multiply, you will get the 12-bit output. Yeah, so that's all from me. Thank you.
For part 2, we need to design a digital system that detects a password. If it's correct, it will give output high for 3 clock cycles. From the digital system requirement, we have select more finite state machine as the base design to this digital system. First of all, before start to write the Verilog, we must provide a state diagram for this system. The state diagram is designed for a password detector that detects 1011 binary bit. It has 7 states from state 0 to 6, where at the state 0 to state 4 is work as a detector, and after the password is correct, the current state, which is state 4, it will continue to state 6 to give output high for 3 clock cycle. Another thing for the detector state, at every state, if the input is not correct, it will go back to the wait state, which is state 0. That's for the state diagram design. Let's continue to the Verilog design and simulation.
We're using the FSM more function where we use the header of ID detector, and in the header let's input password, clock reset of clock valid password, and we use 3-bit of the register where we want to store if each of the bits in this register, so it can move sequentially every step smoothly. Yeah, we use the function of case to move one bit into to move bit from the from state 0 until state 6. So each bit that we have entered will be follow the master clock of the positive clock trigger. It means when we entered 1011 and each bit 1 0 1 1 and each bit will be get as input at the positive edge clock, right? And when we use the function register in touch band, we use function initial beginning clock and use 30 seconds, means into 39 seconds, and wait for 39 seconds and we'll reset and it will begin. So this is more where the output function will be depend on the current state. So we will get the output. So when we here this is the we put clock upward and reset upward, and we will see how the system will be the password will be detected correctly. So here we will see the each bit which has been detected correctly by the Cisco detector correctly. So we put in 1011 in every positive edge clock, and once it detects a final bit of 1, the output, the system will detect the ID or the ID correctly, and it will give the output of 1. So it's mean, let me see, it will give the valid password of 1, mean it will goes high at the positive edge clock in 3 clock cycles. This is 1 clock cycle, 2 clock cycle, and 3 clock cycles. Yeah. So the output, the system will generate the output of in a 3 clock, the output of high in 3 clock cycle when the system correctly